Hello everyone. Today let's solve the problem queries. Right. So this was asked on KTU programming camp day 5. Right. So some camping was going on, I think. So in that they have asked the question queries. Right. Question queries. The first one. So you can just go through the question. You can just go through the question. This was mainly boot camp, I think. I don't have any idea. So yeah, this was asked on basically KTU programming camp. So this is fine. You can just go through the question. The question is very easy to understand. I'll just summarize the question so that it will be easier for us to solve the problem, right? So what the question states here, we are given an integer array. So this one, we are given an integer array, right? So again, I'm telling we are given an integer array of size n, of size n, and a number m, of size n, and a number m. So we have to process q queries of the following types. What we need to do, we have to process the q queries of the following types. This is completely related to queries, man. As the question name itself indicates that this is related to queries. So whenever I remember queries, I think of three things. One is segment tree, one is Fenwick tree, another one is parse table. Uh, if you want to go with a basic optimization or intense or extreme optimization, my mind goes into this one, these three things, data structures. One is segment tree, one is Fenwick tree, and another one is parse table whenever we are solving the problems on the queries, right? So we are given an integer array of size n and number m. We have to process q queries of the following types, right? So let's see what are the this one, three types. What are the types basically, right? So one is plus PR. One is plus PR. What is plus PR? This increases the array of P by R and print the new value. This increases the array P by R and print the new value. So that's what it indicates. It increases array P, this one, array P by R and print a new value. The second one is minus PR. The first one is plus PR. The second one is minus PR. This decreases the array of P by R and print the new value, right? We have to skip if the result is less than 0. I'm just saying this is important part. We have to skip if the result is less than 0. Another one is this one, plus PR, minus PR, S, L or mod. So this the query might contain S, L or mod as well. So LR is nothing but the left, right? So this is mod. S, L or mod. So S is nothing but the sum basically, right? So if a query is starting from the S, this is nothing but the sum left, right, mod basically in simple terms. So we have to print the sum of all the elements from index L to index R, where element modulo M equals mod, where element M equals mod. Equals means comparison operator, value, mod, this one, element M equals mod, right? So again, let me read out the question loud so that we can just hop into the input output part next. Just listen to this carefully. So we are given integer array, this one, of size n and number m. We have to process q queries of the following types, right? So we have to process the q queries of following types. One is plus PR, minus PR, second one is minus PR, and the third one is SL or mod. So plus PR means we are increasing, this one I'm speaking of plus PR, right? So we are increasing array P by R and print a new value. Second one, minus pair, we are decreasing array of P by R and printing the new value. Third one, SLR mod. So this one, SLR mod. So this one is we are printing sum of all the elements. S indicates sum of all the elements from index L to R, index L to index R, left, right, basically, where element modulo M equals mod. M equals mod. So we are comparison value. So M value has to be equivalent to mod, right? So this is about the question basically, right? So we just have to process the queries of these types, these three types, plus PR, minus PR, SLR mod. So in the queries, it can consist of the plus PR, minus PR, or SL or mod, right? So let's see the input output part, man. See here, we have been given in the input, so we have been given n. This is nothing but the n. They have said in the question that we will be having the array of size n and this one, right, number m. So this is nothing but m, and this is nothing but the array. So we have been given integer array, right? So this is the array, right? So this 3 indicates that we are having 3 queries. So this is nothing but the queue. So we are having 3 queries. This you can, by saying seeing it itself, you can say that this is SLR mod, right? So it is starting from the S, sum, right? So basically SLR mod means we have to print sum of all the elements from index L to R, where element modulo M is equivalent to the mod value, right? So this is nothing but SLR mod. So this one L value from index 1, this one R value index 3, and modulo value they have given 2, right? So this is plus PR. You can just see here, this is plus PR, nothing but this one 2 1 plus 2 1 value, right? So we have to increase the array of P by R and print the new value. So this is nothing but the minus PR. This is nothing but the minus PR. So we have to decrease the array of P by R and print the new value. And if we have to skip if the result is less than 0. We have considered this one, and this one, this is fine. Finally, output that we need to get here is 231. So the output that we need to get here is 231 for the queries S132 plus 21 and minus 12. So we have to process these 3 queries S132 plus 21 and minus 12, right? So the output that we need to get here is 231. Simple one, very simple one basically. So this is the first question, right? So the question will be quite obviously very simple, right? Very simple question. So this is fine. And now let's move on with the approach part, right? I hope the question is completely clear along with the this one. What do we call? Along with the input output part, right? So now let's move on with the approach followed by the complexities, and then let's write the code as usual. First, let's move on with the complexities part. Sorry, let's move on with the approach part. So here I have considered the same first example that they have given in the question. This is nothing but N, this is nothing but M, this is nothing but the array, and this is nothing but number of queries, and this is nothing but this one query 1, query 2, and this is nothing but query 3. So we have to process these 3 queries, right? So we have to process these 3 queries, and the output that we need to get here is 231. Output that we need to get here is 231, right? So let's move on with the step-by-step explanation here. First, we have n equals 3 and m equals 4, right? So first here itself we have n equals 3 and m equals 4, right? So initial array we have been given in the input 1 2 3, the second line, right? So we will be going with a 1 based indexing here. Array of 1 equals 1, array of 2 equals 2, array of 3 equals 3, right? So this is simple. So again, array of 1 equals 1, array of 2 equals 2, array of 3 equals 3. So we will be considering this one as tree of 0, tree of 1, tree of 2, tree of 3, right? So basically we'll be going with a 1 based indexing. So we'll be considering from 0 to 3 basically, 0 to 3 basically, and we'll be going with a 1 based indexing for the this one. Array consists of the elements 1 2 3. Array of 1 1, array of 2 nothing but the indexing, right? Array of 3 equals 3. So now we will fill the trees based on the array of I module m. Array of I modulo m. Modulo m means array of I is nothing but first we will be considering the value 1, second we'll be considering value 2, and the third will be considering value 3 here. So first modulo m means here m we have been given 4. M we have been given 4. So in the question itself we have considered that we'll be going with a array of I modulo m, right? So the same thing, we will fill the trace based on array of I modulo m, right? So here array of 1 is 1, so we'll be going with the 1 modulo 4, right? 1 modulo 4, that is equivalent to 1, that is equivalent to 1. This will be going with a, so one more thing I forgot to tell you here, we will be going with a approach binary index tree or the BIT, right? So we'll be going with a binary index tree, BIT, or the Fenwick tree, right? So we'll be making use of the Fenwick tree to solve this particular problem, right? So this will be array of 1 modulo 4. Next array of 2 modulo 4, quite obviously the solution is 2, right? So 1 modulo 4 1, 2 modulo 4 2 we got. So again we'll be going with the update basically, as we are as we'll be making use of the BIT, or as we are making use of the BIT, so we will be going with the update method. So here we will be going with the update as well as the query, I think. So these two methods are required, right? So build is not required. Let's see further. So here, yeah, uh, tree of 2 dot update. So this will be 1 comma 1, as we got this one array of 1 and the solution 1, as we are going with the array of I modulo m, we got 1 here, so this will be 1 comma 1. Array of 2 is value 2, and we got the solution 2, and tree 2 dot update, this will be 2 comma 2. So we got 1 comma 1, 2 comma 2. Same goes with 3 comma this one, array of 3 as well, because we have got the value 3. This will be 3 modulo 4. We have got the solution 3, and tree of 3 dot update will be 3 comma 3 itself, right? So value and the solution that we got, so 3 comma 3. So now we got 1 comma 1, 2 comma 2, and 3 comma 3 based on the array values, right? So now each binary index tree tracks the sum of values at indexes where array of I modulo m equals mod. So this we have already discussed, we don't have to discuss again. So let's go with the query 1. Query 1, here in the question what they have given, SL or mod, right? So this is nothing but L, this is nothing but R, this is nothing but the mod value. This is this indicates plus PR as per the question, and this indicates minus PR, as per the question, right? So this is fine. So now let's go with the query 1, nothing but S132 here. So what we want here, we want sum of array of I where 1 less than or equal to I and 3 less than or equal to I, right? So this one will be array of I modulo 4, nothing but we will get the value 2. We will get the value 2, right? So current array we got here is 1 2 3. So array they have mentioned in the question is 1 2 3 itself, right? So only array of 2 is 2. So the value of array of 1 is 1, array of 2 is 2, and array of 3 is 3, right? So only the value of array of 2 is 2. This satisfies the 2 modulo 4, that is equal to 2. Nothing but we are going with the array of I modulo m. This has to be equivalent to the m value. So array of we got the value 2 here. Array of I modulo 4, this is 2, because we are going with sum of array of y where 1 less than or equal to I less than or equal to 3, right? So this has to be quite obviously 2. 1 less than or I has to be less than 1, sorry, I has to be greater than 1 and less than 3. I has to be greater than or equal to 1 and less than or equal to 3, right? So the value is 2. We have got the value 2 here, and one second, sorry, and here the current array value we have got here is 1 2 3. Only array of 2 equals 2 here within the arrays, so the value, so this satisfies 2 modulo 4 equals 2. So the result we have got for the first query is 2. For the result that we got here for the first query is 2, right? So output for the first query is 2. Let's move on with the second query. So now for this one, this is nothing but the plus pr, right? So we will be going with the array of 2. Array of 2 equals 2 again plus pr. So here p we have 2. So we will be going with the array of 2 equals 2, nothing but 2 plus 1, nothing but 3 here. In this case, plus pr, right? So we have to increase the array of p by r. We have to increase the array of p by r. Minus, for the minus pr, we have to decrease the p by r. So increase p by r. We have been given plus pr here. Based on what we have discussed, increase p by r means 2 plus 1. So we have to increase the 2 by 1, right? So when we increase the 2 by 1, we get the solution 3, right? So now we have to update the binary index tree, remove 2 from the tree 2, right? So this will be tree 2 dot update 2 comma minus 2. So quite obviously this will be 2 minus 2, and we will be adding 3 to the tree 3, right? So this will be, again we'll be going with the update operation is very important for this particular problem. Tree 3 dot update, this will be 2 comma 3. Now array becomes 132, quite obviously, right? So now array becomes 132, which consists of 3 elements. So the output will be quite obviously 3. The output will be quite obviously 3. So after updating the binary index trees or the fenwick tree, we have got the output 3 here. So why we have went through this step? Array of 2 equals 2, 2 plus 1 equals 3. So p value is 2, and we have to increase the p by r. We have to increase p by r, and r we have the value 1 here. This is nothing but plus p r, right? So this is nothing but p, this is r. We have to increase p by r. Nothing but 2 plus 1, we will get the value 3, and then we are updating the bits here. So we have to remove the 2 from the tree 2. So because we are having the 2 as p, we have to remove the 2 from tree of 2. This will be tree of 2 dot update 2 comma minus 2 we have got, right? So now we have to add the 3 to 3 tree 3. This will be tree of 3 dot update nothing but 2 comma 3. So now array becomes 132. So the output will be quite obviously 3. Output will be quite obviously 3. For the second query, we have got the output 3. For the first query, we had got 2. For the second query, we have got 3. Right? So let's move on with the third query. Now for the third query, we have minus PR. Minus PR. So we have to decrease the value of the P by R. Whenever we have been given minus PR, we have to decrease the value by this one r, right? So we have to decrease the array of p by r. Here minus 1, as we have to decrease the value of p by r, this will be my this one my sorry 1 sorry minus p r 1 minus 2. This will lead to 1 minus 2. As we are decreasing the value of p by r, this will be 1 minus 2. So 1 minus 2 will lead to minus 1. So minus 1, in the while reading the question, I had said you one thing, if you remember correctly. So if the value means we have to decrease the array of p by r if we are going with a minus pr, and we have to print the new value, and we have to skip the result if the result is less than 0. Here we have got the value minus 1. What we need to do, we have to skip the value, we have to skip the result, sorry, if the result is less than 0, right? So invalid, this is invalid because it would become negative. So we skip the update, and we will just return the output 1, and we will just return the output 1, this one itself, p itself. We'll skip the update, and we will just return the value of p, in this case 1. So for the third query, we have got the output 3, right? So for the first query, we have got the output 2. For the second query, we have got the output 3, and for the third query, we have got the output 1, based on SLR mod, based on plus PR, and based on minus PR, right? So the output that we got here is 2 3 1. This is the output that we got accordingly with the criteria or the conditions that they have given in the question, right? So here the output that we got here is 1, which is equivalent to the output that they have mentioned in the example 1, right, within the question. So our approach works absolutely correct. Our approach works absolutely correct in this case. As we are completely familiar with the approach, let's do one thing. Let's move on with the complexities part. Let's move on with the complexities part. So what would be the time complexity here? The time complexity would be q of logarithmic n, right? So we are processing the q queries, and each query takes logarithmic n. So to solve the problem within the logarithmic n itself, we will be going with per query, we'll be going with a usually fenwick tree or the binary index tree, right? So that is the reason we'll be going with a fenwick tree or the segment tree for the intense optimization, right? So when the constraints are tight, usually we'll be going with a this one fenwick tree or the segment tree, right? So here each query takes big of logarithmic n. Just give me a second. Here, this one. Each query takes big of logarithmic n due to the bit updates or the prefix sum. So total it would be q. Each query takes logarithmic n due to the bit or the binary index tree updates or the prefix sum. So obviously we have to calculate the prefix sum, right? So for calculating the prefix sum itself, we make use of the bit or this one segmented. So here each query takes big of logarithmic n due to the bit updates or prefix sum. So total time complexity would lead to big of q into logarithmic n. Simple. So what would be the space complexity here? The space complexity would lead to big of n into m. Why? Because we are storing m bit trees, which where each is of size n. Each of size n, basically, in simple terms. We are storing uh, m bit trees, each of size n. So overall space complexity would lead to big of n into m. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of q into log n and big of n into m respectively, right? So now we are done with the complexities part. As we are completely familiar with the complexities and the approach, we are good to write the code. Let's start writing the code. So let's start writing the code, right? So we'll be going with the fast input and output. For that, I'll be making use of the input output package along with the utilities package as well. We will be making use of the different utilities. So I'll just go with import java dot input output dot star. This is fine. Import java dot util star. So the next part here would be, let me go with the class main. So I'll just go with public class main. So you can just give any name to the class. So I have just given main. So that is relevant to the problem basically, right? So as we had discussed earlier, so we'll be going with the fenwick tree or the binary index tree class. So I'll just go with static class fenwick tree, right? So fenwick tree. So within the fenwick fenwick tree class, let me go with long tree here. So this is fine, long tree. And also here, let me go with the size. Let me go with the size. So this is fine, man. Just give me a second here. 1 second. Yep. This is fine. Let's go with the initialization part. So this will be. Did I give just Fenwick? Oh, 1 second. Let me make this one Fenwick tree. I had left the space right here. So this is fine. Fenwick tree. Let me pass the parameter n here. Let's initialize size to n plus 2. And also let's go with the tree equals new longer size. This is fine. Yep. Let me come out of this one. So let's go with a point update. So here we have to add the delta to the index I. So I'll just go with void. This one will be void. So let me go with the update. Let me go with the update method here. This will be int I, comma delta, which is of the type long. So this is fine. We have already discussed that we'll be going with the two methods basically. One is update and another one is query. I had mentioned during the approach, I had mentioned that update is the very important method, right? So that will be making use of the fenwick tree class, right? So let's see what we'll be doing in the update. So basically we are going with a point update here. We have to add the delta to the index I. So I'll just write the simple while loop here. This one will be I less than size, when I has to be less than size. So let me go with iterated value of the tree equals tree of I plus delta. So this one will be delta. This is fine. Next one is we have to move to the next one, right? So we have to move to the next index. So I equals I plus I ampersand minus I, pure Fenwick tree, right? So pure Fenwick tree. So this is fine. We are done with the update method. Next, let's go with the query method. Nothing but we are going with the prefix sum up to I, right? So we have to go with the prefix sum, nothing but up to I. So I'll just go with long query. So this one will be int I, right? So within the query method, what I'll do, let's initialize the sum to 0, man. First, I'll just go with sum equals 0 while mm, while I greater than 0. So this is fine. And let me go with sum equals sum plus tree of I. This is fine as well. So let's move to the parent. Let's move to the parent. This will be I equals I minus I minus I. So this is fine. So we are done with this part almost. We have considered sum. We are going with the prefix sum. We have to return the sum, right? So I'll just go with a return sum. We are done with this. So let me come out of this one entirely. Let me come out of this one entirely. So now let's go with the range sum, nothing but L comma R. So I'll just go with a long range. This one will be the query range, query range So this one will be int l comma int r, int l comma int r. So this is fine within the query range method. So let me return here query of r minus query of l minus 1, right? So we are done with the this one, what do we call, Fenwick tree class. We are done with the Fenwick tree class. So now let's make use of it within the main method, right? So here I'll just go with main. So let me delete this one, man. So we'll be going with the input output exception as well. So let me go with here throws input output exception. So this is fine. Yeah, this is fine, man. Within the main method, what shall we do? Let's go with the buffered reader for the fast input. So I'll just go with buffered reader br. This one will be new buffered reader input input stream reader. So this one will be system dot in. So this is fine. Next one will be buffered writer. So I'll just change the reader to writer here. So this one will be buffered writer, buffered writer, or I would have considered print writer. So this is fine. PW. Let me go with BW buffered writer. So this will be new buffered writer, new output. Sorry. So this has to be output basically. Stream writer system dot out. So this is fine. So we are done with the buffered reader and writer. So we'll be making use of the string tokenizer as well. So I'll just go with the string tokenizer here. Let me go with a SNT new string tokenizer. This one buffered reader dot read line. So this one will be read line. So this is fine. We are done with the buffered reader, buffered writer, as well as the string tokenizer part, right? So now accordingly with the input, if you remember, we went with n and m, that is fine. Then next we have to go with the array size, right? So array size, I'll just go with array size is nothing but n itself. So int n and m we are going with array. Sorry, we have to go with nm for the first line input within the input. So I'll just go with integer. This is integer, right? So let me make use of the parse int here. Parse int, we are making use of the string tokenizer. So variable name I have given st here, st dot next token, next token. This is fine. The next one is int m equals integer dot parse int. This is also fine. St dot next token, right? So this is also fine. So we went with the array size and mod value range, nothing but 0 to m minus 1, right? So n and m. Next, we have to go with a one indexed array to match the binary index tree or the Fenwick tree, right? So next line was for the array basically, if you remember the input. So this will be new int of within the array. I'll just give n plus 1. This is fine. We are just considering the one indexed array to match the BIT. Next, let's go with the Fenwick tree. So let's create the instance of the Fenwick tree here. We have already written the Fenwick tree class, right? So I'll just go with a variable name trees here. This will be new Fenwick tree. Let me pass m here. Let me pass m. So this is fine. This is fine, man. Yeah. Now let's go with the iteration part. So we have to consider individual queries, right? So I'll just go with int I equals 0, I less than m. So this will be I plus plus. So this will be trees of I. This one equals new Fenwick tree of n. This is fine. Yeah. We are almost done. So now we have to read the initial array values. So initial array values in our case, in the example one, they had given 1 2 3, right? So we have to read the initial array values. So we have considered this one string tokenizer, the variable st have considered. So I'll just, let's create the string tokenizer instance here, string tokenizer. So this one will be buffered reader dot read line. This is fine. Is this correct? I hope so. So let's go with a for loop here. So this one will be int I equals 1, I less than or equal to n, I plus plus. So this is fine. Within the for loop, what shall we do? We have to read the value and we have to update the correct mod tree. So first let's read the value. So this one will be array of I equals integer dot percent. This one will be string tokenizer dot next token. So this is fine. This will be trees array of I modulo m. This one is fine. Dot, let me go with the update part here. I pass I comma array of I. So this is fine. Yeah, we have read the value and we are updating the correct mod tree. So we are done with this part. So let me come out of this one entirely. Now let's go with the so we have to go with the number of queries as well. So we went with nm, we went with the initial array, this one initial array. uh, then we had the queries, right? So number of queries mentioned, and then we have to process the queries. That's what we did. That's what they have given in the input, right? So here first let's go with the number of queries here. As I've said in the this one question, this is q equals, I'll just go with the q equals q variable q here. For the number of queries, I'll just go with integer here, percent, as it is an integer. So again we have to read. I'll just go with a buffered reader dot read line. Yeah, this is fine. This is correct, man. Buffered reader dot read line. Yeah, we have just successfully read the number of queries. Now let me make use of the string builder instead of the string tokenizer. So I'll just go with the string builder. So this is fine. Output equals, let's create the instance of the string builder. So here the string builder, this is fine, man. Let's move on with the further steps. I'll just go with a while. So we have to process the test cases. So I'll just go with greater than 0 while loop. First, what we need to do here, let me go with the string tokenizer equals, let's create the instance of string tokenizer. This one is fine. Buffered reader dot read line. So this is fine. The next thing is we have to go with the operation type. So I'll just go with the, let me just go with the string here. For the operation type we have to go, I'll just go with the variable op here, st dot next token. So this is fine. So the next value here would be, let me go with a simple if condition here. If operation dot equals, so this one of s. So this one, what shall I do? So within the if condition, let's go with the query sum. Let's go with the query sum of l comma r within the array for the values equals mod, right? So slr mod plus pr and the minus pr we need to consider, right? Within the query, for the integers we have to go with the slr mod, and there are three types of queries. One which is of the type slr mod, s sum, we have to sum l comma r, right? So from index l to index r, and finally we have mod value as well, that is slr mod. And another one is plus pr and another one is minus pr, right? In the minus pr, if the value goes below 0, then we have to skip that one and just return the value p, right? So that's what we had discussed in the approach. So I have given operation equals s. Basically we are considering slr here. So we have to query the sum of l comma r for the values equals mod. So let's move on with the same thing. So I'll just go with int l equals, so this one will be integer dot percent. So this is fine. percent of string tokenizer dot, I'll just go with the next token here, next token. So let me copy the same thing for R and mod. So let me paste this one twice here. So let me change this one to R. Let let me change this one to mod. This is fine. This remains same, integer dot percent of string tokenizer dot next token. So next, what we need to do, we have to append the output. So we have to append this one to the output. So I'll just go with output. We have already considered output variable. So let's go with append. So this one will be trees of mod. This is fine. Dot query. This is fine. So we have written query range. So we'll be making use of the query range for L, for this purpose itself. We have written the query range method, right? So I'll just go with, we need to append. I have already made use of the append once. This will be, output has to be in the next line. So I'm going with a slash in here. So else we have plus PR or the negative PR, right? So we have plus or negative operation. We have plus or the negative operation here. So let's go with the PR along with the plus or minus, plus or the negative, positive or the negative operation. First, let's go with the PR. So int p equals, so I'll just go with the integer. So let me copy the same thing, man. I don't want to copy this one. So I don't want to type this one. Sorry. Let me copy this one. Let me paste it over here, right? So int p equals, again int r equals, so this one again integer dot percent string next token. This is fine. So let's go with old value. So this one will be array of p. This is also fine. And int new value. So this is equals to operation dot equals, we have already made use of, right? So if it is equals to plus, if it is equals to plus sign, then we'll be going with a, we have to print old value. Also we have to append the r here, right? So this is fine. Else we have to go with old value minus r. So this will be old val minus r, right? So this is fine. We are done with the this one, plus or positive or the negative operation, nothing but plus PR minus PR in the input, if you remember, right? So this is fine. So next we are left with only one thing, I think, or yeah, if the subtraction would result in the negative, then we have to skip, right? So for the uh, minus PR, if the value is negative, so in this case we have got the value negative, right? So here for this one, minus 1 2, so we have got the value negative 1 minus 2, right? So 1 minus 2 modulo 4, so it the value went to negative minus 1. So what we did, we skipped the value minus 1 and we returned the value 1, the value of the p instead, right? So that's what we need to articulate in the form of code now. So this will be, if the subtraction would result in negative, then we have to skip. So I'll just go with if p dot equals here. So this is fine. Negative, negative, and new value. If it is less than 0, then let's go with output dot append here. So this one will be old value again, append. So this has to be in the new line. So let me go with slash in here. This is fine. So let's go with a continue keyword. So we have to skip, right? So to skip, we'll be making use of the continue keyword that the Java provides. So this is fine. Let me come out of the if condition entirely. Now we are left with only certain things basically. So first we have to remove the old value from its mod tree. So this is required. So let me type this one quickly. So this one is related to input output. So this will be old value dot m. So we have made use of the update method within the fenvic tree. So we are making use of the update method here because we have to remove the old value from its mod tree, right? So for that we need the update operation here. So this will be p comma minus old value. So not ola value. So this is old value. So this is fine. Again, this is a what is happening. So this is fine. Now we have to update the array as well. Nothing but array of p, right? So array of p equals, we have to update this one with a new value. So this is fine. We have done that. And finally, if you remember, we have to add the new value to the correct mod tree, right? So how can I articulate that one in the form of code? In the form of code. So I'll just give here trees of new val. This is fine. Modulo m. This is also fine. So this one, let me go with the update. So this is fine. P comma new val. P comma new val. So this is fine. So yep. Again, now we are left with the append part only to the output. So I'll just go with the output dot append. So this what we have to append. We have to append the new value, and we have to go with the next line. So I'll just go with the append, again append keyword. So this will be slash m. Simple, simple, right? So I'll just come out of this one entirely. So what we are left with, basically we have to output all the results, and basically the final step would be we have to flush the output. So these two things we are left with. So first let's output all the results. So I have went with the keyword bw for the buffered data. So I'll just go with the buffered data dot write. So this one we have made use of the string builder. So I'll just go with the output dot to string to string. So this is fine. This is fine. Yeah. So finally, let me go with buffered data dot flush. We have to flush the output, right? So as we are making use of the fast input output, nothing but buffered data and the print writer or the buffer writer, so that we are getting from the input output package. As we are making use of it, we have to flush the output. So I'll just go with the buffer writer dot flush, or you can just go with the buffer writer dot close as well. Both are same. You can just go with the close or the flush here. So I'll just go with the buffer writer dot flush. So we are done with the code. So before checking the code with the different inputs, uh let me copy paste the signature starter template, right? So just give me a second here. So let me come here, let me paste it over here. So this is fine. So let's concentrate on the logical part. Let's check the code with the different inputs, man. So here for this one we have been given only one example, so we have to get the output 231. Let's check. I hope this works, man. So we have the errors here. So instead of ampersand I have given 7 here. So this is pure by this one within the fenvic tree where it is 43, line number 43. So this one has to be ampersand. Yeah, this is fine. Now the error has to be gone. Yeah. Mm, oh, we have 6 errors. So here, incompatible types int cannot be converted to the int. So where it is, somewhere I have done the wrong thing. So let's check. In the line number 61, right? So we are going with a int array equals new int this one. So yeah, here I have not mentioned the. Just give me a second here. Yeah, I have not mentioned array this one, I think. Just give me a second. Yeah, here I have not mentioned the array symbol. So this one has to be int array equals this one new int of n plus 1. This is nothing but the one indexed array, right? So we are making use of the, or we are going with the one indexed array to match the binary index tree here, line number 61. So this error has to be gone now. Yeah, this was causing the problem basically. This was the main thing. So we are getting the output 231, right? So we are getting the output 231. So uh, the output that we need to get here is 231 itself, right? So we are done with the coding part, right? So we are getting the desired output. Let me copy this one entirely. Let me come here. Let me click on the submit button. Let's go to the submission part. So let's do one thing. We have to copy this one, right? So let me copy this one. Uh, problem number from here 100741. So let me remove the slash here. So this one has to be queries, a queries as well. Let me paste it over here. So this is fine. Now again, Let me copy this one entirely. Let me paste it over here. Let me hit the submit button. Right. So I hope this works for all the test cases, man. So this is not showing here. Let me go to profile. So yeah, here you can clearly see here, right? It is running on the test one A queries. So let's wait for some time. So for certain problems, we have to consider the problem number from here, right? So yeah, here you can clearly see here in the toast it is showing accepted. So let me come here. Yeah, accepted 233 ms. This is fine. So whatever the code that we have written works absolutely correct for all the test cases, right? So let me click on this one, main fin victory. So yeah, this is the one we have just written, right? So whatever the code that we have written works fine for all the test cases. We have went with the pure BIT, pure binary index tree, or the Fenwick tree to solve this particular problem, right? So we are done with the solution part. I hope the solution part is completely clear along with the complexities and the approach. For now, this is it. Thanks for watching, guys.